So for this video, we'll be showing a proof on how to get the theorem that we used in the previous video, prime or composite hat. So let's start. So our theorem states that a composite number n has a prime factor that is at most the floor square root of n. So this is the theorem that we used in the previous video to determine if a number is prime or composite. So moving forward, just a disclaimer. Note that in proving this theorem, we will use some advanced techniques only seen in higher level math. So say we'll probably be using this symbol, which simply refers to implies. We'll also be using the idea of proof by contradiction, wherein we'll be first assuming the negative or the contradiction of what we want, then we show that that is impossible. So that would lead to our desired outcome to be the only possible. So say if our desired outcome is A, we first assume negative A. We show that this is not possible. So A is the only possible outcome. So similar to that. And we'll also be using the concept of without loss of generality, which is useful when there are multiple cases with similar way of proving. So to simplify things, we just state without loss of generality. So these are some methods that will be probably using for our proof later on. So moving forward, we first state a lemma. So when we say lemma, this is something that is essential in proving a theorem. So it's like a theorem that will be used in another theorem, but we state it as lemma. So lemma states that every integer n greater than 1 has a prime divisor. So intuitively, say if we have the numbers, if we have say 3, 7, 4, 8, 10, we know that through prime factorization, we can decompose this one into 3 times 1, since these two are primes. This can be decomposed in 2 times 2 times 1, 2 times 2 times 2 times 1, and this can be decomposed in 2 times 5 times 1. So in this 3, observe that we can write all of this with a prime divisor in it. So we won't be proving this one since we'll be focusing more on our actual theorem. So just take note of this lemma. So let's start proving our theorem. So first, in proving, we first check what we are given. So this one, a composite number n, will be taking advantage of this idea of composites. And what we need to show is this one, that this n has a prime factor that is at most the floor square root of n. So this is similar to saying, this refers to equivalent. This is equivalent to saying that, say, if this prime factor is p, then p is less than or equal to square root of n. Since at most, so the highest value of p is only this one. So this is what we need to show later on. We use this to show this one. So let's start the proof. So proof. So first, suppose that n is a composite number. Similar. Is a composite number. So when we say n is a composite number, this refers to as n is equal to, say, x, y, wherein x and y are elements of natural numbers, since we're dealing with positive numbers out here, and x and y are between 1 to n. So we just state this since the idea is that x and y are not only 1 and n, since if x and y, if x is equal to 1, then y is equal to n, so that implies that n is prime, but that is not what we have stated here. Since we know that n is a composite number, we must be able to write n with factors wherein x is not equal to 1 or not equal to n, and same goes for y. So that's why we state it as this inequality. So what we need to show is that either x is less than or equal to the floor of n, or y is less than or equal to the floor of n. So this one. So since we don't have much space, we'll bring that to the next page. So first, proving by contradiction. Let's suppose that not this one. So x is greater than. Let's start first with n, since it would it's easily to put this later on, since we are dealing with integers. So let's suppose that x is greater than n and y is greater than n. So this implies that if we multiply these two, then x, y is greater than. Oops, I'm sorry. There's something incorrect. We must not forget this. There is square root here. So this one and this one. So we know that when we multiply them, this one is n. But note that what is xy? Xy here is equal to n. So this one is n. Now observe that this implies that n is greater than n, which is absurd. This is a contradiction, since n can't be greater than or equal to n. I mean, it can't be greater than n. It can be greater than or equal to, but there's no equal to here. So this is false, which then implies thus x is less than or equal to square root of n, or y is less than or equal to square root of n. Now observe here, then since we are dealing with integers out here, we can simply put the floor function out here. So the idea is, say if we have 6.25 out here, so this is the square root of n. So if we get the floor function, it's simply 6. So since the highest value for x, since we are dealing with integers, possible for this one can't be 7. Since if it is 7, then it violates this inequality. So even though if we write this one as 6, it does not change the fact that the maximum value for x will only be 6. So whether we put a floor function or not, since we're dealing with integers, it does not matter. So that's something to take note. When dealing with integer, the floor function can be put on or removed, especially in inequalities, just to take note. So now that we have this, since there are two cases, if we focus on this one, then we will have a proof out here to get the answer, and if we focus on this one, we also have a proof here to get the answer. But that would just be a bit long if we repeat the process, so we use the idea without loss of generality, since we're just dealing with arbitrary elements here. So this is fine. So without loss of generality, suppose that this one, since we're dealing with OR, this one is the element that is less than or equal to the floor square root of n. So we have cases. Case 1, if x is a prime factor, then we are done, since we have shown that this one, a prime factor, is at most the floor of square root of n. Prime. So this is done already. Done. Now case 2, what if it is not a prime factor? X is not a prime factor. Now if x is not a prime factor, then we know first that from over here x is greater than 1, which implies that we can use this lemma, since x is in n, wherein n is a subset of integers, which is indeed true, since n deals with only positive integers, while this one deals with positive and negative. So we can apply the lemma out here. So this lemma states that every integer has a prime divisor. So we know that, let's state that out. Since x is greater than 1, by our lemma, x has a prime factor. Now, say this prime factor, say, let's denote it by, say letter P, has a prime factor P. So, this implies that P is less than or equal to x, which is, we know that it's less than or equal to the square root of n. Now, this is true since we know that the factor is less than or equal to the number that it is a factor in. So this inequality holds, and this one is equal to the inequality firm assumption. So we know now that P is less than square root of n. Now are we done? Not yet, since we only know that P is a prime factor of x. We don't know if P is a prime factor of original, which is n. So let's move on to the next page. Let's bring this. I guess let's bring this case. Oops. Let's bring this case to the next page. So we have something to start on. So again, what we need to show is that P is also a prime factor of n. So now take note that n is equal to xy. But since we know that P is a factor of x, then we can write this one, x equals P and K, with K similar to this one, but we won't state it anymore. So x is equal to P, K. So this one is equal to P, K, Y. Now what can we see here? Let's write it over here. N equals P, K, Y. We can see here that P p is a factor of n. Is it a prime factor? Well, definitely, because if it is a prime factor in x, then it is also a prime factor in n. Obviously that won't change. So say if you have say if we have 8 and it has a prime factor of 2. If we have 4, clearly 2 is still a prime factor. So we know that it does not change whether p is a prime factor or not. So this will always be a prime factor no matter what happens. But we have shown that this one is a factor. So we have shown here that indeed p, this is simple to conclude. So p is at most the floor squared of n, where p is a prime divisor of n. So we have shown that indeed in either cases, whether in this one or this one, we have shown that a prime divisor of n is at most the floor squared of n, no matter what happens. So to conclude our proof, we must never forget this symbol since it is used in all proofs. This square, or we could also put this one, but I prefer the square, or whatever say, I prefer the square. So we have proved that this theorem is indeed true. So that is all for this video.